SwayamPrabha. Digital India. Educated India.
Hello and welcome to the 9th lecture of the machining science course. So, let me remind you that we have discussed the Merchant circle diagram and how to find out the stress, strain rate, okay, and how to find out the angle, which is the shear plane angle, and how to measure the shear plane angle and how to analytically find out the shear plane angle. I would like to make a small correction here, that in the shear strain rate we said that this is delta S by delta Y into 1 by delta T. So, we can write this not like this, but delta S by delta T. I am correcting that, please make that correction, delta T. This is actually the Vs, right. This is the Vs and this will be instead of delta T, therefore, it will be divided by 1 by delta Y. So, please make this correction, that this can be written as delta S by delta T, which is Vs. That is how we can find out this is the Vs, and this has to be instead of delta T, this has to be therefore delta Y. Okay. So, what we can find out is the finally the shear strain rate is equal to Vs divided by delta Y. So, if we know the Vs for any given delta Y, you can find out what is the strain rate. So, now based on whatever we have discussed so far, I would like to discuss some of the numerical examples, so that you could find out that how the Merchant's theory or whatever we have learned so far can be applied in practice. For example, a mild steel workpiece is being machined at a cutting speed of 200 meter per minute with a tool which is given in this way. So, this is, if you understand that this is in the ASA, if you remember we have discussed it, it is in the coordinate system. So, this is the back rake, side rake and so on and so forth. So, all these angles are given, 6 angles, and this is the tool nose radius in inch. The depth of cut and the uncut thickness are 0.5 millimeter and 0.2 millimeter respectively. If the average value of coefficient of friction between the chip and the tool is given to be 0.5, and the shear stress of the work material is 400 Newton per millimeter square, then determine the shear plane angle and determine the cutting and the thrust component of the machining force. We know the Merchant's first relationship. So, from here we can say that the this also we can know that this is tan inverse of mu, this is coefficient of friction, which is given as 0.5. So, we put the value of 0.5 and we find out what is the value of the lambda, which is the friction angle. By the way, there it was beta, but this is the friction angle, lambda here it is made. So, from here we can find out that the phi is equal to 90 minus this is given as the phi, all right, and phi we can find out from this value, sorry, this is given as 26.57 we found out is the lambda, and this is the rake angle. So, the rake angle is given as the 8 degree. Now, why not to take that 0 degree? Because this is the back rake angle, this is the side rake angle, and as you understand that the side rake angle we said it influences the cutting force and the power, not the back rake angle, remember that. So, therefore, the alpha s is taken as the alpha value and this is put in here as 8 degree. Lambda we found out as 26.57, we have put it in here. From the Merchant's first relationship we can find out the phi. We have to find out the phi because then the Fs will be according to the formula that we have seen earlier. W is d by sin gamma p, we have seen that also in the cutting diameter. This is the plane like this, okay, shear plane, and here we have said that this is the D, this is the depth of cut, or this is equivalent to also we said the T1, this is in the orthogonal case, all right. This is the tool, and here we said that the width would be the width of the material, all right. So, therefore, W will be the depth of cut divided by sine of the gamma p. Gamma p is the principal cutting edge angle, and if this is the tool, then this is the principal cutting edge and this is the gamma p. Okay. So, therefore, from here we can find out what is the value of the W, that is the width, and knowing the width all other values are given, T1 is given, tau s is given, phi we found out, and we know that then Fs will be this. If we know the Fs, then the resultant force R from the Marchants we can find out, which is equal to Fs divided by this. You remember that we said Fs is equal to R and the cos of phi plus lambda minus alpha. This is the friction force, there friction angle, there we said as beta, by the way, okay. The same thing, beta or lambda. So, this is the friction angle. Now, from here we can find out what is the resultant force. If we know the resultant force, all right, and from here we know the formula of the Fc and the Ft, again from the Marchants, all right, then the Fc can be found out as R into cos of lambda minus alpha. R we found out, lambda we found out 26.57 and alpha is given as 8. So, this is the Fc. Ft will be R of this, and R we found out, lambda we found out, alpha is given. So, it can be found out. There is an alternate way, you can see that this way also you can find out, the result will be the same. That is, you take the formula which you have derived during the Marchant circle diagram discussion, and from here all these values will be known, because Fs we found out, put the value of the Fs and so on, and you will find out that these values are the same. So, this is an alternate way of solving this problem. Next example, problem 2. During orthogonal turning of a mild steel workpiece of 20 millimeter diameter with the 150 rpm and with a 0 degree rake angle, the forces normal to the shear plane and thrust are found to be 85.6 and 35. Normal force is 85.6 Newton and thrust is 35, thrust force. If the chip thickness is twice the uncut thickness, estimate the power consumption in watt. Now, first let us find out what is the cutting velocity. This is pi d n, all these are given. So, it will be this value, okay. Either it is in meter per minute or you can convert it into meter per second. Then Fc, which is from Marchants, okay, this formula, because the Fn is equal to Fc sin phi plus Ft cos phi, we have derived that. From here the Fc is equal to this is given, that chip thickness ratio is 0.5 because the chip thickness is twice the uncut thickness. So, it is this. Therefore, for 0 degree rake angle it is given here, all right. We can find out that tan phi is equal to R, which is 0.5, which is we found out from here. Therefore, phi is equal to tan inverse of 0.5 is 26.56 degree, and then we can find out the Fc, because the Fn is given, Ft is given, phi we found out, okay, and we can find out therefore the value of the Fc. Vc we found and Fc is here. So, product of this and this will be the power. So, this is in Newton meter per second, which is watt, okay. And there is an alternate solution. You can also see that this way, using the Marchant's diagram or the Marchant's formula, we can also find out, and the result will be the same power. Third problem is, for an orthogonal cutting, the following data are given: cutting force is given, thrust force is given, rake angle is given, chip thickness and width of cut, shear plane angle, these are given. Determine strength of the workpiece material, friction angle without using Marchant's first relationship. Okay. Now, the phi we know that we have derived this formula. From here we can find out that what is the value of the r, which is 0.419, here it is coming, which is T1 by T2. This is the chip thickness ratio we are talking about, r. Now, it is given that T2 is 1.5 millimeter, T1 is this therefore, and because r we found out. So, chip thickness ratio into the T1. So, this is T into T2, sorry, this is the T1. So, therefore, the area is this, which we can also find out as 3.088 millimeter square, and then the Fs can be written in this way. This is the formula taken from the Marchants, all right, and we have the values known, FCFT, phi is known. Therefore, the strength of material will be Fs, force upon area, which is the strength, and we know the Fs, we know the As, we can find out the strength of material. Fs we can find out from here. This is given how to find out the Fs, because we found out here. F is equal to Fc sin phi sin alpha plus Ft cos alpha. This is directly taken from Marchants, and all these values are now known. We can find out what is the value of the F, which is the friction force and the normal force. Okay. So, therefore, friction force divided by normal force will be the coefficient of friction, and here the mu can be found out by F by N. Hence, the friction angle, which is the lambda, tan inverse of mu, which is this. So, whatever has been asked, this we found out simply here, knowing the the relationship that we have already derived earlier. Okay. Next to this, we will be discussing another model, which is based on another principle rather than the Marchant's principle. So, once again let me remind you that the Marchant's principle is based on the minimum power consumption, okay. And here this is thin zone model also, because they are assuming that the deformation is occurring in a thin zone, and as I have said earlier that normally the plastic deformation occurs in a zone and not in a plane. Okay. So, they are saying that this zone is very thin and this can be assumed to be a plane, like in the Marchants. So, this solution is based on the following assumptions, that the deformation takes place under the plane strain condition. Deformation occurs in a thin zone, as I said. So, this is another assumption. This is the shear plane and not the shear zone. The workpiece material is rigid, perfectly plastic, and its behavior is independent of temperature and strain rate. This is the third assumption. Next, they are assuming that the inertia effects are negligible, which is the steady state deformation. Tool tip is sharp, that means there is no nose radius, and the continuous tip is formed. All right. Stresses are uniform on the rake face, as in case of the Marchants. So, as you can see that this is also a 2D, I mean this is not a 3-dimensional, it is a 2-dimensional, because they are saying that the tool is sharp, mu is constant, okay, and the stresses are uniform and so on. Now, the cutting forces are transmitted here. What is the principle is this: cutting force are transmitted through the triangular plastic zone ABC, okay. Meaning that they are saying that if there is a resultant force acting on the chip from the workpiece through the shear plane, for this to be transmitted towards the rake face of the tool, it has to go through a triangular plastic zone ABC, where no deformation occurs, because they considered that there must be a stress field within the chip to transmit the cutting forces from the shear plane to the tool face. Once again I will explain it to you. The resultant force has to be transmitted from here to here. Okay. Now, this transmission can take place through a plastic zone where no deformation occurs because of this force, then only this can be transmitted. If this force creates deformation, it will be absorbed. So, therefore, they are saying that this is the ABC is the plastic zone where the material is plastically deformed to the maximum. Okay. In the ABC, the entire material is in the plastic state, stressed up to the yield point. yield point B in that diagram that we have discussed in the very beginning. Shear plane AB, this is the shear plane, is a slip line since maximum shear stress occurs here. As you can see that AB is the shear plane, and we said that the maximum shear deformation occurs along the shear plane. Other slip lines must be perpendicular to this line. Okay. These lines are also the slip lines, because this is maximally stressed, as we said, ABC. Okay. This is the plastic zone within the chip through which the forces are transmitted from the work to the tool. Okay. BC, this one, is the free surface since no force is transmitted to the chip after it has crossed the line BC. You understand what we are saying is that this is maximally stressed and the force is transmitted, that is it, up to here, and then there is no force transmitted there. The chip is moving, okay, because of the force transmitted up to this. So, BC is the free surface since no force is transmitted to the chip after it has crossed the line BC. Slip line must meet this surface at a 45 degree. This is the slip line theory, and in the theory you can find out that the free surface here BC makes an angle of 45 degree with the slip line, that is the AB. AB is the slip line that makes an angle of 45 degree with the free surface, which is BC. This is according to the slip line field theory. Alright. So, we are not discussing the slip line field theory in details. So, this is the application of the slip line field theory, which is called the Lee and Shaffer relationship. So, they have taken a principle which is different than the principle taken by the merchants and Ernst. Here they are saying that there is a slip line field theory, and according to that there will be a stress field through which the forces are transmitted from the shear plane to the rake face of the tool. Okay. Now, if we have this, then the Morse circle construction, Morse circle diagram you all are familiar with, is a convenient means of relating stresses on any plane to the principal stress. So, I have also shown it to you that the Morse circle diagram is placed on the center, is placed on the normal stress or the direct stress, and perpendicular to that is the shear stress. All right. Now, since plane BC is a stress free, Morse circle must pass through the origin B. So, as you can see that if it is a surface plane BC, the stress can be given and as a point here on the periphery. This is the 2D, and I showed it to you earlier also that in the 2D case it can be shown on the periphery of this Morse circle. So, this BC stress on this is B, which is located here, because it is a stress free. All right. There is no stress, 0 normal stress, 0 shear stress. Point A, C, D, F are displaced from B by 90 degree. Which are point A, C, D and F? These are here. So, this is the A that you can see, this A is here, okay. D is this plane, okay. This plane is F, this plane is accordingly. So, these are the planes A, these are the lines either vertically here or normal to that this. These are displaced from B by 90 degree. Okay. This will be twice the angle of physical plane. Here it is 45 degree. So, therefore, in this the A, D, C and F, they will be from B, they will be at a 90 degree angle. They will be inclined displaced by a 90 degree angle. Now, E, this is E, okay. This is inclined to face D, this one, sorry, this is E and this is D. D is inclined to E by an angle of phi minus alpha. You can find out that this angle is phi minus alpha, because this is the rake angle, this is the shear plane angle. So, this angle will be phi minus alpha. Let us say this is nu, nu is equal to phi minus alpha. So, if it is nu, therefore, in the stress plane the angle subtended by the arc AE, this one, this will be at the center, which is the 2 nu. Okay. So, this angle is the 2 nu angle, because the nu we are saying that this is the nu, okay, phi minus alpha. This is with respect to the point B. So, with respect to center, this angle is the 2 nu or the 2 phi minus alpha. Assuming uniform stress tau and normal stress sigma on the rake face, the friction angle we can find out here, and this will be the tan inverse of lambda by tau by where it is here. From this you can find out that this is the value, and this will be equal to the E s, okay, E s divided by S into B. So, this divided by S into B, this is related to the tan of this, and tan of this is equal to the mu. So, you can find out the mu, which is F by n, okay, and F by n will be here. Therefore, EOS, this is the point, EOS, this angle plus this angle is 2 mu or the 2 phi minus alpha. This is equal to, see here, this is nothing, EOS plus this is the angle we mean to say, okay, do not confuse that. This angle plus this angle is equal to 2 lambda, you can see that, all right. This is 2 lambda at the center, because here it is lambda. So, 2 lambda plus 2 nu, or nu is equal to phi minus alpha. So, therefore, this is equal to pi by 2, and this makes 2 lambda plus 2 phi minus 2 alpha is equal to pi by 2. Okay. So, this is the equation which is derived by the Lee and Shaffer, and you can see that this is very close to the Merchant's relationship, although the Merchant's relationship is based on the minimum power consumption during the machining process. Okay. And here in this case, the Lee and Shaffer says that there should be a stress field through which the forces are transmitted from the shear plane to the rake face of the tool. So, I once again would like to repeat that here what is happening is that this stress field is made. In this stress field, these are all the slip lines where the maximum deformation occurs, okay. And each of these lines is given a name, like for example, this is D, E, A, B, C, F and so on. So, here they are all maximally deformed, and they are making an angle of 45 degree with the free surface. So, therefore, in the Morse circle it will be twice that, which is 90 degrees. So, therefore, we said that A, D, C and F, they are from the B, okay, they are at a 90 degree angle. Now, then what we said is this E, this one is inclined to this by an angle of nu, and here it will be the twice the nu, 2 of this, and then if you sum up this angle and this angle, which is 90 degree, from here you can find out this relationship. So, the relationship is not a very difficult to find out, only thing is that you have to construct the Morse circle diagram from the stress field and the machining diagram that the Lee and Shaffer has proposed. Now, please all the time you should also keep in mind that this is valid only when these assumptions are met. If any of these assumptions is not meeting, in that case the Lee and Shaffer relationship will not be valid. Okay. After that, we will be discussing the topic which is the friction in metal cutting. Okay. Why we are discussing this? Because in the normal case, when we have the sliding friction, there the F and the N, because of the normal force, the friction force F. So, the F by N we always assume to be constant, that means the F is proportional to N. This is what happens in the case of the sliding friction. we will see in the friction in metal cutting through a model that how it differs in the case of the metal cutting and how it differs from the sliding friction particularly, where the F by N remains constant. Let us see this. See the nature of sliding friction, if we have to consider that. In here we have to mention that since the solid surfaces have asperities, for example this. So, when the two surfaces meet each other, they will actually not meet along the area which is the real area, but they will be meeting at some point on the asperities, as you understand this. Okay. The real area of contact differs from the apparent area. Apparent area is the geometrical mating area. In case, so therefore, what we are saying is that the real area of contact, this is different than the area of contact on which they are meeting, because they are meeting on the asperities and not the full area. Okay. So, therefore, the real area is different from the geometrical mating area. In case when the load increases, the asperity deformation becomes fully plastic and the real area of contact is then a direct function of the applied load independent of the apparent area or the geometrical area of the surfaces. So, what is said is that when the load is increasing, then these points on which the two surfaces are meeting on the asperities, they become initially elastically deformed, and then as the load is increasing further, the elastic deformation becomes plastic deformation. In that case, the real area of contact is then a direct function of the applied load N, and this will be independent of the apparent area of geometrical area of the surfaces. So, we can write down that AR, okay, which is the AR is the real area of contact, all right. That is what we said, that the real area of contact is directly proportional to N, which is equal to N by the yield stress of the softer material. Out of these two, whichever is the softer material, the yield stress of that material has to be considered. So, therefore, the real area of contact will be equal to the N divided by yield stress of the softer material. Now, during sliding, shearing of the welded asperities occurs. The mechanism described by the adhesion theory of friction, meaning that once the normal load is applied, as we said, that asperities become so to say welded, because they are the normal force is increasing, and then when two bodies move on each other with respect to each other, these asperities, welded asperities will be sheared off, okay. And this is known by the adhesion theory of friction. Now, the adhesion theory of friction will give you an equation of the F, that is the friction force, is equal to tau into AR. AR is the real area of contact, and therefore, mu, which is F by N, this can be given as tau AR divided by N, we found out as the AR into the yield stress of the softer material. So, which is nothing but AR is getting cancelled. So, the tau divided by yield stress of the softer material, sigma y. So, this equation shows that mu is independent of the apparent contact. So, that is the basic idea in the case of the normal sliding friction, when the two materials slide on each other, and then this how it can be applied to the machining, and how the mu happens in the case of the machining, that we will be discussing in the next class. Thank you for your attention.